Good morning, class, and welcome to this lesson on pressure and depth in a static fluid. Static fluid. We are now going to derive the equation for pressure and depth in a static fluid. So we're going to derive an equation, and we're going to give some conceptual examples as to how this equation applies. And so let's first talk about what static means. Static fluid means the fluid is not moving or flowing. The fluid is not moving or flowing. Okay, so this is almost like a cup of water sitting there, or like a big lake. It's sitting there. There's no currents. It's just a static fluid. And we know that molecules are moving and vibrating, but we're not going to take that into consideration. We're looking at the fluid as a whole, and as a whole, it's not moving. So let's draw a picture of a fluid here. Okay, now this fluid has a density. This fluid has a density. It is sitting on top of an area here, and it is a certain height. It is a certain height, okay? So we want to derive an equation between pressure and depth. Pressure and depth, okay? So let's first discuss what pressure is. Pressure is equal to force over area. Force over area. But how do we get force of a fluid, especially when we're dealing with a large fluid? Well, we would then need to break force down into mg over a. Okay, mg over a. So force is just the weight of gravity over this area, okay? Well, once again, how do we find the mass of a fluid? It's kind of difficult. Well, fortunately, we can relate mass of a fluid because we know the equation for density. Density equals m over v. So that means m equals rho times v. So why don't we plug that in to right here? So we're going to have rho times v times g over a. Now, for any of you who have ever studied geometry, which I'm sure are pretty much all of you, volume and area are very well related. Area would be like looking at this shape right here. We're looking at the base and the height, or the base and the width. And then if we want volume, we just have to add one more dimension. We have to add one more dimension of height. Okay? So volume is like base times width times height. So volume can further be broken down into area times the height. Just like area is 2D, and volume is 3D. So we have area here and the height, and so volume is the same thing as area times height times g over a. So if you notice here, area cancels out, and we have the pressure of a fluid is equal to rho g h. So the pressure inside a fluid, if we know how deep something is, we know the density of the fluid, and we know gravity, and we're probably going to do all these problems on Earth, we know if we, at any point, at any height, we know the pressure at that height. Because we know the density, we know gravity, and we know the height. So pressure is equal to rho gh. Now, I'm going to expand this just a little bit further. This pressure right here in blue is equal to the pressure. This is the pressure, and we'll say this is water. Let's say this is water. This is the pressure of the water, okay? Rho gh. Is that all the pressure? And the answer is no, because there is still air. I'm going to draw little dots here for air above this, and this air exerts pressure in all directions, and it's exerting a pressure down. So there is a fluid on top of this fluid. So if we want the absolute pressure, okay, I'm going to put P absolute. We have to add the PO, which is atmospheric pressure. Okay, PO is pressure of the atmosphere plus rho gh. And that's if we want the total pressure. Maybe we do, or maybe we don't. It all depends on the problem. But the reality here is we have the absolute pressure at the bottom is equal to the pressure is equal to the atmospheric pressure plus rho GH of this fluid here. Okay, so this is going to be our main equation for a lot of things. However, I'm going to expand this just a little bit further, and just change it slightly, and say P2 is equal to P1 plus rho GH. Why did I put P2 and P1? Well, let's take the same fluid over here. The same fluid, okay? The same fluid, and let's say this fluid is inside a system that is larger. So there's more fluid around here. And I just want to know the pressure differences. And so this is P1, this is the top surface, and P2 is the bottom surface. So I'm not dealing with atmospheric pressure. I'm just dealing with what's the difference in pressure here versus here. Well, if I just want to know this, atmospheric pressure doesn't apply to this question. But it's still the same issue. I have a pressure of the fluid exerting on top, and then I have the pressure on the bottom. So what is this pressure on the bottom? Well, it's the pressure of the fluid on top plus all of this right here. So it doesn't have to be just the atmosphere. It can be anything. And so in general, this equation can really apply to any situation. And if we want to know the pressure difference, we subtract P1 from both sides, and we get P2 minus P1, which is kind of the same thing as saying delta P is equal to rho GH. So this might apply depending on the question that we're given. And so we just have to read the question carefully and practice looking at questions like this to figure out what equation we need to use. These are very, very similar, but a little bit different. So that is the derivation of the pressure equation. Pressure is equal to rho GH, and if we want absolute pressure, it's equal to atmospheric pressure plus rho GH. And in general more, the pressure at the bottom is equal to the pressure at the top plus rho GH. So let's look at some pictures here. I'm going to make some general rules right now. Okay? I'm going to make some general rules about this. So the first general rule is that pressure is exerted in all directions. And second general rule is that pressure depends on height. Okay, so if we look at this picture here, this is a picture of the Hoover Dam. Okay, Hoover Dam, Lake Mead. Okay, and we can assume there's a lot of pressure up on the other side of this dam here. Okay, so this dam is holding a lot back. And so if we posed a hypothetical situation that, let's say this picture down here, this image, has the same height of water that's right here, the same height of water, but there's no Lake Mead. So pretty much we chop it off right there. We just have this water right here going down. The question is, do we still have to make this dam just as strong? And the answer is yes. Okay? Because the pressure depends on height, if this column of water has the same depth as this water right here, it doesn't matter what's behind it. It doesn't matter. So if this has the same height, pressure is going to be exerted in all directions, and it's going to exert on the dam just as much as it would with this entire lake sitting behind it. So once again, pressure depends on depth, pressure depends on height, and pressure is exerted in all directions. Okay? So let's take a look at another example. An example right here of A and B. The question is what has a greater pressure, if you're at point A or point B? Point A is directly below the surface, and point B is kind of under the land right here. And the reality is that the pressure of A equals the pressure of B, because the pressure at A is the same depth as the pressure at B. It does not matter that there's this land above it or whatnot. These two have the same depth in this water. Pressure is exerted in all directions. Therefore, pressure at point B is equal to the pressure at point A because they have the same height. Okay? Because pressure is exerted in all directions and pressure depends upon height. Okay? Here's another example. Which one of these figures, A, B, C, or D, have a greater pressure? Which one of these have a greater pressure? And the answer to this is A equals B, which equals C, which equals D. It doesn't matter if it's a thick tube or a swirly tube or a tube with two knobs in it or a regular thin tube. Pressure depends upon height. These all have the same height. These all have the same height. And pressure is exerted in all directions. So, and at this point, pressure is being exerted down. Okay? So it doesn't matter which one is which. It only depends upon height. So this is another example of our rule being here. Pressure depends upon height. Pressure is equal to rho GH, and the absolute pressure is equal to atmospheric pressure plus rho GH, or in more general, P2 equals P1 plus rho GH. This is a good example of this formula right here. P2 minus P1 equals rho GH. The question says, this question is in your book, and this question says, how much greater is the pressure at your feet than at your heart? How much greater is the pressure at your feet than at your heart? Well, there's a much greater pressure in your feet than in your heart because the blood in your feet is 1.35 meters below your heart. But if we want to find the pressure difference, we're going to do P2 minus P1. This being P2 and your heart being P1. Notice we're not taking into account atmospheric pressure. We're not taking into account atmospheric pressure because we're just looking at what's inside the body. But P2 is going to be the lower point and P1 is going to be the upper point. And so we can solve it with this right here. And P2 minus P1, in this situation right here where someone's laying down, the pressure in your feet equals the pressure in your heart. This is why when you go home, people always say, put your feet up, kick your feet up, because when you put your feet up, you relieve the pressure in your feet because there's no longer this pressure difference. It's just zero. Now, what I'm saying, and what I'm not saying is, if you lay down, you have no pressure in your blood. You still have blood pressure because that's how it works. You still have blood pressure. You just don't have a pressure difference between your heart and your feet.